have P signal that the pressure is coming to blow the blower. The blower expands, pushing the knob to the left side. This pushes the lever towards left side, and knob 2 is being pulled, wobbling the gateway for the high pressure source to go out. That's the working of the system. Proportional to the signal pressure, the output pressure varies. Proportional to the signal pressure, the output pressure varies. So you will see that if this is sinusoidally, you vary your input signal, the output signal also varies sinusoidally. Okay, possible. The output pressure that is varying proportional to, I said you come this less. Close the door. You have output pressure that varies proportional to the input pressure. Output pressure that varies proportional to input pressure. So there is a 1-to-1 scaling. Now, proportional to input, the output is varying. To call a device an amplifier, we said 3 things. What are they? Huh? It should use its own, not its own, external power supply. The amplitude should get magnified. Huh? The power level is supposed to be increased, isn't it? So here, if you look at the power level, hydraulic, pneumatic power, next class maybe. Pneumatic power, we said pressure times Q, that's input. Calculate for the input as well as for the output. Here it is lower input, here it is higher output. So you will be witnessing that power level is increased. It uses external power supply, and whatever is the input variation, you get output variation here. So the power level is amplified, amplitude is increasing, external power supply is used, faithful reproduction will be, forgot to say. Whatever is the variation in the input, the same variation you witness in the output. So that's a faithful reproduction in the output. So this device can be called as even an amplifier. Okay, you simply put everything inside the box, and you have this as input, this as output. All your conditions are satisfied for an amplifier, so we will call this as an amplifier. Okay. Now, anyway, that we have discussed last class. But today we are going to keep this as a template to understand the transistor-based amplifier. Okay, here of course you might have learned transistor-based amplifier as part of your basic electrical course or electronics course. I don't think anyone comes to this level of engineering without understanding or without learning the amplifier, but it's a big brush up. So you have from where there are 3 ports. Which are the ports? One port is through that, the spool is being actuated towards left or right. That's swapping the valve position at the output. Through the port, the output is being emitted, is called emitter. Through the port through which you collect your source power supply is collector. Okay. So you collect your high power from here, emit your the output through that port. So the port that is used for emitting the output is called emitter. You need an external power supply. Through the port you collect the external power. That port you call it as collector. And how much of collector power is to be emitted is decided based on the input that you receive from this port. So it is called base. It is a base which is the basis for giving the output, proportional to the, of course, input. Okay. So you get 3 terminologies out of that. This is collector, this is emitter, this is base. And you have heard about PN junction, and you have a P-type material and N-type material, and join it together. A junction is formed, and that junction is PN junction. If you have 2 of one type material and 1 of other type material, you can connect it in combination and you form a transistor. It's a triode, 3 electrode device. Okay. Here you have let's say N-type material, P-type material, again N-type material. So it is NPN transistor, or you can have P-type, N-type, and P-type, PNP transistor, whatever it is. So you have actually a tryout device where you have two type of material, but three elements that you take form a device that's a transistor. Okay. Of course, there are other conditions. I am telling very basics of that. Okay. So now, what we call these device, the symbol of these device, can be put like this. This also has the same terminology. You see, the power supply will be connected here, so it is collector through which you get your output. It's emitter, and how much collector voltage or current that goes to emitter is decided by the signal that comes here. So that's why it's called base. You have collector, emitter, and base. Same idea. And of course, here you have N-type material, P-type material. P-type material is connected to positive, N-type material is connected to negative. So this P-type to positive, N-type to negative, the bottom half portion, the junction, the PN diode, okay, is connected in forward bias or reverse bias. P-type material to positive, N-type material to negative. It is forward bias. Okay. When it is forward bias, what will happen to the resistance between the P-type and N-type material? It will increase or decrease? Decrease. When you connect a PN junction diode in forward bias, it will start conducting more. We'll put it like that. It will start conducting more. You connect a 3 volt, 1.5 volt battery, there will be some voltage setup, the current will flow. You put 3 volt, still more current will flow. So as you increase the potential, if you increase the potential here, more current will flow, more voltage difference. I mean, the resistance reduces proportional to the voltage that you have here. You are all aware of these ideas? You already learned, right? Okay. So this voltage, as you increase, I am not happy with the way you do this. You have P-type material, N-type material, and you have a junction. Okay, that junction is a barrier for the flow of charges. That junction is big, the barrier is big, not junction. The barrier is big when the voltage is small, when it is forward biased. As you increase the voltage across the forward bias voltage, the barrier keep on reducing. That means resistance keep on reducing, and resistance decreases means more current will flow. Is that clear? Right. Now look at the top half of it. P-type material is connected to negative, N-type material is connected to positive. So the top half of the transistor is connected in forward bias or negative, what is that? Reverse bias. It's connected in reverse bias, isn't it? Which bias? Forward bias means N. Good. So reverse bias means how will you connect? Positive will be connected to negative. That is not positive. N means? N-type? N-type material. Okay. And negative to that positive. And negative terminal to P-type. You know why I asked you this question, right? Because you are not mentally here. This position is sleeping position. That I am not interested in the lecture. I am planning to sleep. So N-type is connected to positive, P-type is connected to negative. So the bias is reverse bias. Okay. When a PN-type junction is connected in reverse bias, what happens to the barrier? Barrier becomes more. It doesn't allow the current to flow that easily. Let's say I am increasing the potential difference. Earlier it was 1.5 volt, now 2 volts, 3 volts, I am increasing the voltage. What will happen to the barrier? Barrier will reduce or barrier will increase? Barrier will increase. Barrier will increase. In forward bias, if you increase this voltage, barrier will reduce. In reverse bias, if you increase the potential difference, the barrier will increase. It will grow. It will offer more and more resistance. If it offers more and more resistance, will it allow the current to flow? More resistance means less current. Okay, current cannot flow easily. So it will have resistance. So the beauty of the working of this device lies in this configuration. You have P, N, P or N, P, N, anytime you take, one half is in forward bias, other half is in reverse bias. When potential difference is increasing, one fellow is going to, forward bias is going to allow more current, reverse bias is going to allow less current. Okay? That's the working of this. But the question is, how to use this device as an amplifier. This can be used as a switch, this can be used as an amplifier. But how to use this as an amplifier? Okay. Now, in fact, in today's class, the objective is that how to use transistor in the circuit and build an amplifier out of it. Okay. So you see, there is a signal. There is a weak signal that is to be amplified. This is what it is. This is basically an AC signal. Okay. What is meant by AC signal? With respect to time, the amplitude varies. So it's a dynamic signal. Okay. So it's a small signal, weak signal. Okay. And we are not able to process it like we have discussed in the last class, like thermocouple output. There's a few millivolts only is coming. That is also with respect to temperature, that is varying. Now, with respect to temperature, the voltage is varying. Okay, so it is a small, weak signal and time varying signal. It's not a constant voltage. If I connect a battery, I will get 1.5 volt, probably constant voltage. But I am not connecting it. It's a varying voltage. What I want amplifier to do is, I want similar variation, but in a bigger amplitude, like a zoomed way. I want as an output. Here, this is what I want here, out of load. Across load, I want same shape, but zoomed version I want. That means higher voltage I want, but shape of the signal should not change. I don't mind you using external power supplies. Okay, so this is VCC. Basically, it is 9 volt, 12 volt, 24 volt, depending upon your application. Whatever magnified voltage that you want. So much of, if magnified voltage is supposed to be from 0 to 10 volt, then your VCC should be something like 12 volts. If your magnified voltage that you want is something from 0 to 22 volts, then your VCC will be 24 volts. The normal standard is 6 volt, 5 volt, 6 volt, 9 volt, 12 volt, 24 volt. These are all some standard power supply voltages. Okay. Sir, can I have 18 volt, 17 volt? Yeah, you can have. But standard is this. Like, we have thread, M10 thread, M11, M15, M20, like that. Metric threads are there. Can I not have M12, M13 in between? Yeah, you can have. Custom threads you can have. But if you have standard threads, you will readily you can go to market and buy thread and come. The screws and nuts you can get it. Otherwise, you have to fabricate it by yourself. Same way, you have some VCC standard. Get some voltage you connect. So VCC is connected to collector. Collector is the one through which we connect the power supply. Isn't it? Here also we discussed. Isn't it? Collector is the one through which we connect the power source. So collector is the one through which we connect the power source. So we are connected the power source. Emitter is the one which gives you the output. Emitter is the one which gives you the output. So that I connected to the ground through a resistor. This is emitter resistance. That through a resistor we have connected, and across that resistance we see what is the voltage. Why we put resistance and connect it to a ground, and across resistance we take the output. because current, if I want to measure, I simply connect cut this circuit. One I connect it to ammeter terminal, other terminal I connect it to the other end. That means I connect it in series. I'll be able to measure current. Okay, but I am interested in voltage. I want to know how much voltage is amplified. So only across a terminal, across a device only I can measure. There, this is the potential. Here, this is the potential. What is the potential difference? A pipe is flowing. I want to measure the differential pressure. I want to measure the differential pressure. How do I make differential pressure? I create a pressure difference, and then upstream pressure, downstream pressure we measure, so that differential pressure can be measured. Like orifice meter or venturi meter or flow nozzles, all that, isn't it? Even flow measurement we have learned by creating a pressure difference we measure. Okay, exactly the same principle in electrical domain. You create a potential difference by putting a standard resistance there, and then measure the potential here with respect to here. I want to know what is the potential here, what is the voltage there with respect to ground. Okay, so put a resistor. Anyway, the other end is connected to ground. Ground means zero potential. With respect to that, what is that potential you measure? So it is kind of people get used to it. The people who are in electrical domain. If you want to measure current, simply cut the wire. One end you connect it to the one end of the ammeter, other end you connect to the other end of the ammeter. You can measure the current. You want to measure voltage, you cut the wire, connect a resistor. One end of the resistor you connect it to one end of the voltmeter, other end of the resistor you connect to other end of the voltmeter to measure voltage. So across resistance you measure voltage. Current means simply connect it in series and measure. Voltage you have to measure in parallel. So you connect it like that. So your device comes like this. Why there is a capacitor here? All AC signal I wanted to pass. I don't want any DC component. By mistake, any DC component comes through this. I do not want. Capacitor is a variable resistor. Capacitor is a frequency dependent resistor. In other terms, frequency dependent resistor. Like if the input signal is a DC signal, it won't allow. If it is a slowly varying signal, 1 Hz, 2 Hz, 5 Hz, it will think whether to allow or not. If it is a high frequency signal, capacitor will say, yes gentlemen, please go. Okay, it will allow. Higher the frequency, lower the resistance in terms of capacitance. Capacitor is basically a frequency dependent resistor. It offers more resistance for low frequency signals, and it offers high resistance for low frequency signals. For DC, it won't allow at all. It will say sorry. It won't allow. Okay. So you put a capacitor here. No DC component will come there. Only AC can go there. Okay. And all DC will be grounded. It will all go to the ground and get connected to the ground. Only AC component will go. Why? My signal is AC signal. Even by mistake, any DC noise component gets amplified and comes, I simply wanted to filter out. I want only the AC variation. I want only AC signal and AC variation. Any DC component, I am not interested. So I put a capacitor, and then here also I want to measure what is the voltage. So this is connected to ground, zero potential. This is the potential of the AC component of the amplified signal. So across the load, I measure the resistance. So all these components, why it is coming, you understand. Okay. Here I put a resistance. Why? It's something like this. You imagine your pneumatic circuit. I want to send some amount of fluid to that valve, to this valve. Sometimes I want to control how much pressure I want to send. Sometimes 2 bar, sometimes 5 bar, depending upon the application, depending upon the requirement, I want to control. So what I do, you imagine it is a hydraulic circuit, because in this case it is easy to visualize. You have a tank full of water, the pipe is coming, high pressure water, because from top, let's say from 8th floor to ground floor, the water is coming. You open that pipe, how much fast it will be coming? Because the potential difference is very high, flow will be very fast. I don't want to allow all the pressure to go into the valve and spoil the application. I want to restrict the flow rate. So what will I do? I put a gate valve or I put a tap, isn't it? With tap which I can open slowly, or I can to required amount I can. Valve in hydraulic circuit or pneumatic circuit is equivalent of resistance in an electrical circuit. Valve basically does what? It offers resistance to the flow of liquid or air, whatever it is. It offers resistance to the flow. Same thing, the job of a resistance in a circuit. So basically, I have a huge source of power. Here it is electrical voltage. I have a voltage of large amount of source. The voltage is coming. According to my application, I want to control what is the amount of voltage that should go to the transistor. Okay, according to the design. So I want to decide how much voltage should come here. To control that, I have a resistance. Okay, so I have a resistance here, I have a resistance here, I have a resistance here, I have capacitance here. I think I have given an explanation. Okay, normally, the teachers who taught me, they simply draw the circuit and only explain the operation of it. Okay, knowing the reason is very important. Only if you have some insight on the subject, you will be able to do that. And what about this? What about this? You have a power supply and one resistor, another resistor that's connected to it. That is voltage divider circuit. That is voltage divider circuit. What is voltage divider circuit? So I didn't bring chalk today. Okay, yeah. I have, let's say, 10 volts. Okay, this is the point. This is the point, 0 volt, ground basically. Okay, so now I put two resistances. Let's say R1 and R2, and I take the supply here. I think this I have already taught you guys in the lab or something. Voltage divider for MTech students. Recently I taught somebody. I don't know whether it is you or the other class. Okay, fine. So this is voltage divider circuit. I have 10 poles, and I will be getting some volt here. There is some resistance, some potential is lost, so remaining potential is available here. Then there is some resistance, that potential is also lost, it is at ground level. So zero potential. So let's say this is V out. This 10 volts, the generic name is V in. Right now it is 10 volts, general notation is V in. So what is V out? What is V out?
10 V out.
Sorry? Is it R2 divided by R1 plus R2 V?
Yes, sir.
Am I right? Am I right? Okay. So voltage divider will divide in the ratio of R1 and R2. One thing I am sure, if I put this also 1 kilo ohm, this also 1 kilo ohm, then this reduces to 1, this is 1 plus 1, 2. Half of V in I will get here. Okay, half of V in. 10 volts if I give, what will be the voltage difference between this and this? This will be
5
volts. Okay, 10 divided by 2, 5 volts. Okay. And suppose you put 1K here, maybe 2K, then it will be 2 divided by 3 of V. Isn't it? So you basically decide how much of voltage that you should get here by varying this R1 and R2 combination. This circuit, you are basically dividing this 10 volts. One more thing. 2 divided by 3 is how much? This is 10 into 2, 20 divided by 3, roughly 6.66. Okay, good. 6.7 approximately. Okay, 6.7 volts. So if this is 6.7 volts, and how about this? From here to here, how much voltage will be there?
10 minus 6 point
The 10 minus 6 point volt will be there. 10 minus 6 point volt is
3.3.
Good. So why it is called a voltage divider? I have some voltage, and if I put same resistance, here 5 volt, here 5 volt. If I put some resistance and here some other resistance, according to this ratio, I get a portion here, a fraction here, and the 10 minus that fraction here. Okay, so I have some voltage, I am dividing into 2 according to my wish. I have an equation which can do that, transform that. So this circuit is called voltage divider circuit. This circuit is called voltage divider circuit. Okay. That is okay, sir, but why I should use it in amplifier application? Why I should use it in amplifier circuit? Why I have to introduce that? That comes here. I want to have a sinusoidal variation. This is very idealistic condition. But I want to measure a positive value above some reference value. I want to measure some negative value below some reference value. I want to measure both positive value and negative value. Okay. So now, what I want to do there is, you can have achieved that in 2 ways. Sir, I don't want this voltage divider circuit. No problem. You give one positive 5 volt, negative 5 volt. Anything between 0 to positive 5 and negative 5, you amplify and you get it. There's no problem. But most of the applications that we have, what we do is, let's say this is 0 volts, this is time, this is voltage. Let's say this is 5 volts. This is 10 volts. No, not this is 10. Something. This is 6 and this is 4. Okay. So this is 6 volts, this is 4. Okay. So what I do is, I have some sinusoidal variation. I will use some middle voltage as my reference voltage, above which my input signal will go slightly above, come to my reference voltage, come below, and then below. Okay. So that the variation above my mean voltage, below my mean voltage, this is positive, representing all positive values. This is representing all my negative values. Representing my negative values and positive values. But actual value will be positive only. Actual value will be positive only. This is maybe 4.2 volt, 4.3 volt, 4.5 volt. Here it is 4 volts. Here 5.1 volt, 5.5 volt, top most 6 volt. So voltage variation will be from 4 to 6 only. But if it is 5, that is my reference voltage. 5 means it is 0 for me. Anything above 5 is positive. Anything below 5 is negative. That's the idea people have used. And then, whatever is the voltage that I have here, VCC. For example, 12 volt I am using as a voltage VCC, which is source voltage. The source voltage that I use is 12 volts. Now, 6 volt I will use it as a 0 volt here. I put the same resistance. R1 and R2 will be same resistance. So here I will have 6 volts with respect to ground. This is connected to ground. With respect to ground, what is the potential here? 6 volts. Okay. For an example. Okay. Anything above 6 volt will be
Positive.
Anything below 6 volt will be
Negative.
That's all. But please pay attention and understand. Normally for a transistor, your base voltage should not be 6 volt. It should be much low. Okay? Because that is what is basically governing how much of current is supposed to be allowed to collector to emitter is decided by that voltage only. Okay? So it should not be 6 volt. For an example, I just showed that this is 6 volt and that is above 6 volt is positive, below 6 volt is negative. Just to convey that idea. So don't keep 6 volt in the mind. Keep some reference value Anything above is positive, anything below is negative. That much you fix it now. So you understand why this portion of the resistors are come. It is basically a voltage divider circuit in order to establish some reference voltage above which we have positive value, below which we have negative value, because my input signal is it's an alternating signal, AC signal, basically a time varying signal. With respect to time, it varies. So it's a dynamic signal. So I wanted to have some positive component, some negative component. So I have brought in the voltage divider to create positive and negative components in my circuit. Up to this is clear? Now. Don't worry, I am not going to teach this to you. Now, anyway, that's input for me, not for you, nothing to worry. Okay. So, here is a basic transistor circuit. So far I have explained why these resistors are coming along with the transistor to form an amplifier circuit. Okay. Now the operation of amplifier circuit. Okay, operation of the transistor based amplifier circuit. How it works? Here I have a signal that needs to be amplified. I have connected to the input. Here I have the output. I have connected a voltmeter and measure what is the amplified voltage. Okay. I know what is my input voltage also. I want to know after amplifying how much it comes. So I have connected. And this circuit is now. This is an NPN transistor. See, the arrow mark is outside, and this is a NPN transistor. So here it is negative. Here it is N-type material, P-type material, N-type. So that's how it's connected. Okay. In fact, same whatever we have discussed here, I have connected. So it is NPN transistor, and the positive negative you have to understand. Okay. Here it is easy to understand because it's all battery symbols that we have used. Battery symbols easy to use. The whole trick of simulating this battery signals using this circuit, that's a great design. That's the greatness of this design in this whole process of doing amplification. Understand carefully. If you are not understood earlier, if you already understood, there is a revision for you. If you are not understood, understand it carefully. There is a beauty in this circuit. You see this? This is P-type material base. Emitter is a N-type material. Isn't it? N-type material, this N-type material is connected to which potential?
Ground.
Zero potential. Ground means zero potential. So that is, you consider it as positive or negative? It cannot be positive, of course. You need not call it as a negative, but definitely it is not positive. So see, this positive, negative, several relative. With respect to what is positive, with respect to what it is negative is what that matters. So it's always relative. Okay? Huh? So next time I will see if you continue like that, you know what will happen. Okay? So his attention is more towards outside. Then you did not come inside and sit in the class, right? You should come and sit here to safeguard your own class identity for a long time. So this is connected to a negative. I don't know whether it is negative or positive. I put it why it is negative. Here I have a voltage signal. Okay, let's say here 1 volt right now, the instantaneous voltage. Right now the voltage is 1 volt. Right now the voltage is
1 volt.
1 volt. Here it is 1 volt. Here it is 0 volt. So compared to this is positive or negative? Compared to 1 volt, 0 volt is negative or positive?
Negative.
Negative. Okay. So ground for me is something like connecting it to a negative terminal. This is p-type material. Compared to ground, this is positive or negative? That is positive. Compared to ground, 1 volt is positive, so p-type material is connected to positive. N-type material, emitter, is connected to negative. So the bottom half of the PN junction is forward biased or reverse biased?
Forward bias.
Okay. I said I have connected 12 volt battery. Here the instantaneous voltage is
1 volt.
1 volt. Now take the top half of the PN junction diagram. Collector is N-type material. Compared to 1 volt, 12 volt is a positive or negative?
Positive.
Compared to 1 volt, 12 volt is more positive. So that is positive. Compared to 12 volt, 1 volt is negative. There is no minus sign there. But compared to him, this fellow is
Negative.
It's something like this. The power level wise, of course, students are most powerful, but academically speaking, we don't have powers. You are supposed to say whatever your teachers are saying. Okay, at least as per our common understanding. People are doing or not doing. Suppose dean or pro VC comes. Whatever he says, I will follow. So here I am the boss, and I'll say, man, you sit, you go out, you sit. I am the boss. Comparing to you, I am the boss. But if Pro VC sir comes, I become like this. Sir, yes sir. If AVP man comes, I will be still more bending. So if Chancellor comes, I will lie down because he is my super boss. Okay, he is paying me every month, my boss. So according to him, I am negative. But compared to students, I'll put my hand inside the packet and then say, hey guys, you do this, like this, we can say. The power is relative. Compared to students, we are better off. Compared to my superiors, I am negative. That's the ideology that you should have. And don't take the example per se, that's only to just entertain you. But that's the ideology that you should think to consider whether it is positive or negative. So here 12 volts, here 1 volt. This is N-type material. This is P-type material. Base is P-type material. That is now connected to same 1 volt only. But now it is considered as
negative.
Why? Here it is 12 volts. So this is N-type material connected to positive, P-type material connected to negative. So top half of the PN junction is reverse bias. Reverse bias. Okay. So for a given 1 volt, this reverse bias junction will have certain resistance. This forward bias, here there is one PN junction, that will have some resistance. According to these both resistances, whatever is the voltage coming here, whatever is the current coming here, will be restricted and allowed to come to the outside of the emitter. You just visualize the water flowing through the pipe with the different taps open and closed. This is like one tap, this is another tap, this is the big gate valve, these are two taps. According to these two taps opening, finally you will see a voltage coming out. You will be able to visualize that. If you have better visualization in electronics, that's still more beautiful. People who are not very familiar with electronics, at least visualize in terms of your hydraulic circuit or pneumatic circuit, you will be able to follow better. Now, what happens? Up to this is the forward bias, reverse bias configuration. Any doubt on that?
No, sir.
There is forward bias. Same 1 volt in the base. The same 1 volt is acting as positive with respect to ground. Same 1 volt is acting as negative with respect to source. Okay? Now is the beauty. Okay? Now what happens? The 1 volt, here is 12 volt, here it is 0 volt, and now of course, here some resistance, here some resistance. This is RC. Of course, these resistance are inside the transistor. Okay. Now you see, because RC and RE are all decided earlier, not during the operation. In the design stage itself it is designed, so that will not vary. These two resistances are PN junction resistance. This and this are junction resistances. Okay. Now look at this. When this volt becomes 1.2 volt, because it can go up and down. It's a time varying signal, that input that we are giving. When it becomes 1.2 volt, when it is 1 volt, what is the voltage difference between a collector and base?
11.
12 minus 1, 11 volts. Is the voltage, that is voltage in the reverse bias circuit. This is 0 volt, this is 1 volt. So this is emitter, base voltage is 1 volt. So this is the 1 volt in the forward bias circuit. Is it clear? Any doubt so far?
Okay.
Anybody is not able to follow? Yes or no? Yes. When 1 volt, this is the scenario. Here 11 volt is the potential for this forward bias circuit. Sorry, reverse bias circuit. 1 volt is the forward bias circuit. Okay. Now the 1 volt is now, this is 1 minute earlier, 1 second earlier. Now next second it becomes 1.2 volts. When it becomes 1.2 volts, what will be the potential difference now? This will be 10.8 volt. This will be 1.2 volt. Because it is 0, 1.2. 1.2 minus 0 is 1.2. Right? So here it is forward bias. Here it is forward bias. Correct, no? When voltage increases, more currents are allowed to flow. More currents are allowed to flow. Here it is what bias?
Forward.
Reverse bias. Here voltage, earlier what is the voltage? 11 volts. Now the voltage has reduced. When in the reverse bias, when voltage decreases, what happens to the resistance? Decreases. Okay. Here also resistance decreases. Here also resistance decreases. In both ways, resistance decreases means what? You are opening the tap. Resistance increases means you are closing the tap. Visualize something like that. So in both junctions, in BC junction, BE junction, both resistances decreases. So more voltage, more current is allowed to flow. More current is allowed to flow. You are able to understand? Okay. So here emitter current will be more. Going through the resistance, the voltage will be more. Put the load resistance measure, the voltage. So you have more. Okay? And same story you can repeat it for 9.5, a reduced voltage. If 9.5 volts, the 1 volt, sorry, 0.95. 1 volt has become 0.95 volt. What is the difference now? 11.05 volt. Here it becomes 0.95 volts. Now forward bias voltage reduced. Forward bias voltage reduced means current reduced. Here reverse bias voltage increased. That means current reduced. Here also it is a closing action. Here also it is closing action. More resistance, less current will flow, and the output will be small. As voltage increases, voltage increases. As voltage decreases, voltage decreases. Making use of this forward bias and reverse bias with a common base. And always you see proportional to the signal increase and decrease and increase, you will see a bigger variation. Here it may be from 0 to 0 to 2 volts, that variation will be there, or minus 1 volt to plus 1 volt, the variation will be there. Here you will see minus 5 volt to plus 5 volt, that variation. Same variation but amplified version of it. You look at only input, only output, you see a small signal is getting amplified and it's available as a big source. So you call this device as an amplifier. Also you can apply all three conditions. The shape of the signal is retained, faithful reproduction. uses external power source, so it satisfies the second condition. It amplifies the power level. You can multiply voltage and current of both the signals. Here the power level is small, here power level is high, so power level is amplified, so you call this device as amplifier. Any questions? Any questions? You are able to understand? Okay, very, very important. Now, till what time this class goes? 10? Okay. We need few minutes for taking attendance. We'll stop here.